Understanding Physics, Exponential Decay 3. This is my third video about exponential decay. So we have n equals n naught e to the minus kt. A very useful equation. We can work out n or whatever, x or whatever, at any point in time using this equation. Okay. Now if we take natural logs of both sides of this equation, we get log n is log n naught minus kt, and if we rearrange it, we get log n equals minus kt plus log n naught. Now, does that look familiar? Well, we've got a variable equals minus k times a variable plus a constant. Does it look familiar? It should do, because it's an equation of the form y equals mx plus c. That means if we plot log n on the y-axis and we plot t on the x-axis, we should get a straight line. And the gradient of our line will be, you tell me, and the intercept will be, well, there you go. We get a straight line with a negative gradient because it's minus kt, and the gradient of our line will be minus k, and the intercept up the top there will be log n naught, natural log of n naught. So what? Well, it's a good way of proving if the relationship is exponential. If you've got loads of data and you want to know if it's an exponential relationship, you plot a log graph. If you get a straight line like this, it is an exponential decay. And then also, it's a very accurate way of determining k and hence determining the half-life. If I'm doing an experiment of radioactive decay and I want to work out the half-life, the best way of doing it is to plot a graph of the log of the count rate against time, get the gradient, get the decay constant, and get the half-life from that. It's the best way, the most accurate way, because you're doing a line of best fit. So kind of anomalous results and natural averaging, etc. Now, in A-level physics, there are a couple of situations. I've deliberately avoided these in these videos up until now, but there are two situations where all this exponential decay maths comes in handy. The first one is in radioactive decay. I have done videos about radioactive decay. If you're doing this topic, you should obviously have a look at them. Look at the equations. dn dt equals minus lambda n. Lambda is the decay constant in radioactive decay. It's the probability that an unstable atom will decay in a certain time. N equals n naught e to the minus lambda t. T half is log 2 over lambda. Okay, my decay constant is lambda. A little bit different, but decay of charges in capacitors. dq dt equals minus q over rc. My decay constant here is 1 over rc. R is resistance, C is capacitance. When you do capacitors, this will make more sense, but the equations are of the same form. Q equals q naught e to the minus t over rc. One thing is, with capacitors, we don't use the half-life. We use something called the time constant, which is similar to the half-life, but it's not the half-life. It goes down by a different percentage, not 50%. Here's something that you should do now. This table shows how the value of a car changes from the time it is bought. A nice brand new car in the showroom, £30,000, but then it depreciates pretty rapidly. This is the value against time. The value goes down exponentially. You know, after 5 years, 60 months, it's only worth 4,000 quid. I mean, I would never buy a new car anyway, because I can't afford it, but also because, shut up, get on with it. Right, so put this data into Excel. With Excel, plot a graph of the value against time. Does it look like an exponential decay? Can you get the half-life of the value from your graph? Also with Excel, plot a graph of the natural log of the value against time. Do you get a straight line? Okay, if you get a straight line, you can get Excel, if you do a trend line and show the gradient, you can actually get a value for the decay constant, and you can get the half-life from this. And another, so you've got two values of the half-life. Have a go at it. It will help your understanding of this topic.